Hello, my name is Pedro Ribeiro and I'll be presenting our work, Highly Sensitive Bio-Inspired Sensor for Fine Surface Exploration and Characterization, developed in a collaboration between INESCAM-N, Instituto Superior Técnico and Institute for Systems and Robotics at the University of Lisbon in Portugal, and the Advanced Robotics at Queen Mary group at Queen Mary University of London in the United Kingdom. The ciliary structure is a sensing structure existing in nature composed of two parts, the cilium, the passive part, and the dendrite, an active part that is connected to the cilium. When a force is applied to the cilium, the dendrite sends neuronal impulses to the brain. Equivalently, in our sensor, the cilia are made of a magnetoelastic composite that emits a stray magnetic field. When a force is applied to this composite, the stray magnetic field will deform due to the cilia deformation, and this variation in magnetic signal can be detected by a magnetic sensor placed under the cilia. This work started being developed in 2015 with a fairly larger sensor and using a low resolution giant magnetoimpedance sensor. It was then further developed in 2017 where a better giant magnetoresistance sensor was used and a reduction in size was made. In this work, we further improve on this device by using a tunneling magnetoresistance sensor capable of outputting a greater signal and consuming a lower power. The cilia were thermal treated to maximize their magnetic moment and therefore the amplitude of the signal that is going to be measured, and an electronic interface was developed and implemented to allow for an easier integration with computer-based platforms and robots. Our device has three main components. The first one is the magnetic cilia, which are composed of 35% of an elastomer, in this case we use PDMS, and 65% of neodymium iron boron magnetic particles. This is a mass proportion, and this particular proportion was chosen as it was the one that allowed us to have the most magnetic content inside the composite while still retaining the PDMS elastic properties. We tested three configurations. Configuration A with 3 cilia assembled in a row, with each cilia having 3 mm of height and 400 micrometers of diameter. Configuration B using the same size of cilia as configuration A but in a 3x3 cilia matrix configuration. And configuration C, which uses the same 3x3 cilia matrix configuration as configuration B, but using smaller 1.6 mm height by 360 micrometer diameter cilia. The underlying magnetic sensor is based on the tunneling magnetoresistance effect. The sensing elements in this sensor are a stack of thin films shaped into 2x20 micrometer squared area pillars. When a magnetic field incides on this stack of metallic thin films, the resistance of the whole stack is going to change as a function of the applied magnetic field. Because these are resistive elements, we decided to use a Wheatstone bridge architecture, as it allows us to have a zero-centered response and to smooth out the transfer curve of the sensor, which will facilitate signal conditioning later on. The sensing device by itself consumes a power of 14.3 microwatts due to its having a lot of sensing elements assembled in series on each bridge branch, and it's powered by a voltage of 1.25 volts. Finally, the third part of our device is the analog front end. This will take the signal from the Wheatstone bridge and send it into a filter and a compensation circuit that will condition the signal, which is then sent into an ADC that will apply a gain to the signal and convert it into a digital representation, in this case using the I2C protocol, so this can be connected to any type of microcontroller that supports I2C. This front end uses a power supply of 3.3 volts and consumes 4.9 milliwatts of power when actively measuring the sensor and 13 microwatts of power when in sleep mode. It has a maximum sample rate of 1000 samples per second and can apply again up to 128 times, which results in a theoretical resolution of the front end of 1.2 nanovolts per least significant bit. The device was first tested in what concerns repeatability. For this test, the sensor was placed at a fixed distance from an indenter, and then the sensor was made to move under the indenter back and forth. So first the sensor starts to move under the indenter and the cilia will contact it, and you see a rising signal. Then the device continues to move under the indenter and you should see approximately more or less constant signal while all the cilia are bent in the same way. And then the device comes out from the other side back into an uncontacted position, leading to a drop in the measured signal. Then the same movement was performed in the opposite direction and this whole cycle was repeated 10 times. The dispersion was calculated as the maximum minus the minimum signal measured at a certain position divided by the average signal at that position. And using this dispersion metric, the average dispersion across all the positions measured was of 5%. The sensor was then tested as a topography scanner for both unpatterned and patterned textures. For unpatterned textures, the sensor was brushed against various types of sandpaper, as these have standardized values of surface roughness and approximately random surface topography. The sensor was made to contact the sandpaper and kept at a fixed distance from it while moving at a 1 mm per second velocity parallel to the sandpaper surface. This signal was then, the signal from each type of sandpaper was then separated into chunks, and the standard deviation of each chunk was computed, and this was the value that we correlated to the surface roughness from the sandpaper. The goal here is to see if we can distinguish between the different values of surface roughness with our sensor. So for configurations A and C, we see that there is some overlap between the surface roughnesses that are coarser, so the ones above 23.1 micrometer surface roughness, although there is a good differentiation between the 9.2 and the 15.1 surface roughness sandpapers. Configuration B, although there is shows some overlap between the intervals of confidence between the 23.1 and the 30 micrometer surface roughness, provides the greatest separation between the average value of each type of surface roughness. So this leads us to believe that the best type of sensor to measure unpatterned textures would be a device that has a large area of contact and a bigger cilia size. For patterned textures, a silicon sample with the patterned features with known dimensions was tested. The test was performed in the same way as before, with the sensor being placed at a fixed distance from the sample surface in such a way that the cilia would be touching the sample surface. In this case we chose 1 mm distance, and then moved at a constant velocity of 0.5 mm per second parallel to the sample surface. The slow speed was chosen to enable a higher spatial resolution in the measurement. The sensor was made to scan the sample in this direction, so in the short direction of the pattern features. And two types of features were tested, some with 20 micrometers high steps and others with 50 micrometer high steps. So configuration A was able to distinguish both the 20 micrometer and the 50 micrometer steps, so able to resolve both these steps with a fairly good spatial resolution. We believe due to the smaller area of contact, since it has only one row of cilia when compared to the other configurations. Configuration B, however, could not resolve the 20 micrometer step, but could resolve the 50 micrometer step, although a broadening of the signal could be seen when the sensor passed over a feature. Configuration C was unable to resolve either step. In conclusion, a bio-inspired cilia tactile sensor was developed and optimized with increased performance, lower power consumption, and onboard electronics and digital conversion to facilitate the integration with computer-based platforms and robots. The device was tested as a topography scanner for patterned and unpatterned textures. In unpatterned textures, it was able to differentiate between finer textures, and the usage of larger and a greater number of cilia appeared to improve the performance in this test. For patterned textures, 20 and 50 micrometer topography steps were resolved, and the usage of small contact areas increased the scanning resolving power of the device.